All right, everybody. I wanted to make a quick video to talk a little bit about the problem that you see there. I realized that in lecture 10, I didn't fully explain how to do this problem, and so I've extended the homework and I'm going to show you exactly how to do this problem. And then if you get, there's another problem in the Canvas that looks similar to this, but I'm thinking that if you understand this, then you will be able to understand how to solve the other problem. All right, so first things first, we need to be able to take these distributed loads and turn them into point loads, okay? That's the first thing. So I'm going to do like a pretty bad, okay, number line there. And I'm going to change here and I'm going to label a couple things before we get going. Label B here and label point A here. I need to make this a little thinner here, I think. Let's go a little thinner. Okay, good. We'll go back there. And then what we're going to do is we need to put a few dimensions. Actually, I'll put a few dimensions in here in green. I don't know why that's so thick. I think that should be thinner, but whatever. 1.2 meters right from B to the edge. We're going to say this is here from A to the edge is 0.9 meters. And all the way across here is 1.5 meters. I know it's not perfect how I drew it, but hey, whatever. All right. So we've got that. Uh, what you want to do is you want to look at that distributed load is really three different distributed loads. You've got a triangle, a rectangle, and another triangle, right? So let's take a look first at the triangle that is to the left of point A, right? Whenever you have a triangular distributed load, okay, looks like that, then you have distributed load, you have to remember a couple things. The resultant force, right, is equal to the area of a triangle, 1/2 base times height, okay? So in this case, the resultant force, the resultant force is 1/2 the base, which is 0.9 meters, that's how wide it is, and then the height is 2.4 kilonewton per meter. And that's how you'd work that out. If you do the multiplication, you will get 1.08 kilonewtons, okay? 1/2 base times height. Now, the question is, where do you put that? Where is this located on A? Note that more of the load is closer to A than it is to the end of the beam. So where do we place this? Okay, well, you're going to place it closer to A. But what is that location for the 1.08 kilonewton force? How far away from the end of the beam is it? Well, as I mentioned in the video, I like to think of it as 1/3 from the high side. And you might be like, what does that mean? What is the high side? Well, the high side clearly in this triangle is at A, right? This triangle goes from the left end of the beam all the way to point A. So the high side of the triangle is at point A. The low side is the left end of the beam. 1/3 from the high side means, what's 1/3 of the length of the triangle? Well, the triangle has a base of 0.9 meters. So 1/3 of 0.9 is 0.3. Therefore, this distance here is 0.3 from A, but it's 0.6 from the edge, right? 0.6 from the edge or 0.3 meters from A, right? Hopefully you understand that. Now, we'll jump over to B and we'll do the other side. The other triangle, right? The other triangle on the right side of the beam. Again, it's 1/2 base times height, right? But in this case, it's 1/2. The base is going to be equal to, let's move this a little bit. Okay, good. The base is going to be equal to 1.2 because that's how wide that triangle is from B to the right side of the beam. And the height is still 2.4, right? 2.4 kilonewtons per meter. I probably should put the units on there, but I think you get it. If you do that multiplication, you should get 1.44 kilonewtons. And again, where do you put that? Well, you know it's going to be closer to B than to the end of the beam. But if you use my handy thing, 1/3 from the high side, it would be 1/3 of the whole distance, 1.2 meters, as measured from B. So if you measure from B to the arrow, it's going to be 0.4 meters. But if you measure from the arrow to the edge here, that's going to be 0.8 meters. Okay? So we got that, and that is a 1.44 kilonewton. And then finally, we've got the rectangular force in the middle. Rectangles are pretty easy, just base times height. The height is 2.4. The base, right, the resultant force is base times height. The height is 2.4. The base is 1.5. And so that's 3.6. And you know it's going to be right in the middle, right? 3.6 kilonewtons right in the middle. Okay? So we got that. We've taken these loads and we've replaced them with distributed loads and replaced them with point loads. Okay, that's pretty easy to do. So the question actually asks you for what is the reaction force at A. Okay, we know. Take a look at this bridge, beam, structure, whatever this thing is. Right? We know there has to be forces at A and B that hold up the bridge or hold up the beam or whatever you want to call it, right? Because there's loads down, right? And we know in statics that there has to be the same amount of force up as there is down, right? So how do we do that? Well, I tried to state in the problem, the reaction forces, I'll draw them in red, okay? The reaction forces are going to look like this. There's going to be a reaction force FA that goes up at A, and there's going to be a reaction force here, FB, that goes up at B. This is the base of the bridge, the supports, where they push up on the bridge, right? Because you have to have the same amount up as you do down, right? We know that there's a certain amount of load down from the distributed forces there, right? I probably should label this one here. This is going to be kilonewtons, right? We know 1.8 kilonewtons, 0.08 kilonewtons, 3.6 kilonewtons, 1.44 kilonewtons. Those are all pushing down on the beam. What holds the beam up? Well, reaction forces at FA and FB hold the beam up. So the question is, how do we solve for FB? Okay, well, it's actually really simple because what you could do is actually do this in one equation. Okay, I'm going to have to scroll down to show you everything. Okay, but I'll come back up. The equation would be this. We know that the sum of the moments about point B equals 0. Okay, so we've been talking about moments. We've been doing moments now for a little while. Lecture 7 and 8, we talked a lot about moments. If we can say this is true, and it is, we can write one simple equation to solve for a force of A. Now you might say, why did I choose B? Why did I say the sum of the moments about B equals 0? Well, because force B, FB, goes straight through. It goes straight through B, so it creates no moment. And so it actually sets up one simple equation. So now you ask yourself, what is the moment about B from the 1.08 kilonewton force? Well, the moment about B from the 1.8 kilonewton force, 08 kilonewton force, is its force times its distance to B. Well, how far is it from this force all the way to B? It's a little bit bigger than 1.5 because it's not, it's actually, this is beyond A, it's all the way over here. So if you think about it, because you're going 0.9 and then 0.6, the distance between 1.08 and B is actually 1.8, right? So if you write this out, it's going to be the force B, which is 1.08 kilonewtons, times 1.8 meters, right? And then you ask yourself, how is that going around B? Well, it looks like it's counterclockwise, which we say is positive. Counterclockwise around B. All right. Well, what about FA? Does that create moment about B? Sure it does. How much is it? I don't know. But I can write it very simply as force times distance. FA times 1.5. So, and by the way, that is a negative because it's clockwise around B. So it's negative. So I write minus FA times 1.5 meters. All right, keep going. We're almost done. Now, what's the next force? 3.6 kilonewtons. How far away is that from B? Well, we know A to B is 1.5 meters, and it's halfway. So what's half of 1.5? Well, 0.75, right? So this is going to be 3.6 kilonewtons times 0.75 meters, and it's also going to be positive, right? Because it's also counterclockwise. And lastly, we've got this 1.44 kilonewtons, okay? Again, I don't need to look at FB because FB goes straight through B. So lastly, we got 1.44 kilonewtons. And how far is it away from B? Well, it looks to me like it's 0.4 meters away from B, right? 0.4. And that's going to be negative because it's clockwise. So I'm going to write this. I'm going to write minus 1.44 times 0.4 meters. And I'm gonna, this is all one equation, right? This is, I had to put it on the next line. Actually, you know what? I could scroll over, but then if I scroll over, I kind of lose it too. So I'm just going to put it all on there, right? I say equal to 0. Now I solve for FA. You can do this. And you get FA equals 2.71 kilonewtons. Okay, that's the answer. Okay, so you now have the answer. I gave it to you for the Canvas homework number 5. If you get this problem, you got the answer. Okay, but hopefully you see it, and if you see the other problem that's similar, you should be able to do it as well. Okay, hope this helps.